Okay, welcome back. Just looking ahead at the syllabus, you have an exam on February 2nd and 3rd in the testing center. Just be advised the testing center requires me to put a late fee starting at 2 p.m. on the last day the exam closes. They do this to control crowds because they know that about 50% of you will gladly pay the $5 to have a few extra hours and the other 50% won't, and that way they can plan on who's coming when. Please do not pay the $5 to take the exam. It's not my intent. Let's see, so we are about one lecture behind. We're starting chapter 3 today. We will probably get through some, but not all of chapter 4. Whatever we don't get to will not be on the exam. Yes?
So is the exam only open on the 2nd and 3rd?
The exam is only open on the 2nd and the 3rd. Okay. All right. I imagine you're feeling overwhelmed by now, and I'm not sure what to say, only that it will get worse. Right now is kind of an overwhelming time in my life too. My research lab, well, it requires funding to do research, right? The reagents, the equipment are expensive, and my students need things to do, so we spend a lot of money on solvents and on reagents, and that money's got to come from somewhere, and so far that's been the tax-paying American public. We have a grant from the National Institutes of Health to fund some of our research in peptide and protein chemistry. And that grant is running out, and so we need to submit a new one. The deadline is February 5th, and so but BYU wants it earlier than that, so we can submit it and make sure it gets in. So it's crunch time for me too. That being said, I don't know what to tell you other than to take it one day at a time like I am and hope for the best. If you've emailed me and I haven't responded yet, don't take it personally. It's just I've been somewhat stressed out with the grant, and I will try to get back to you as soon as possible. If it's a really, really burning question, just stop by my office and force me to answer it, and I will. Okay, well, we're beginning chapter 3, and there's two basic things we need to talk about in chapter 3, and that is how to talk about organic molecules and name them, and then non-covalent interactions. A word about naming molecules. First of all, the Smith text does it piecemeal, chapter by chapter. As we learn about alcohols in chapter 9, the Smith text will talk about how to name alcohols. I find it best to just get all of the naming out of the way at first, because doing it piecemeal, chapter by chapter, leads to a lot of redundancy. The second thing I will say about nomenclature is you will always be able to think of a molecule that would be difficult to name. And that's just sort of how it is. It turns out that as we draw larger and larger molecules in organic chemistry and we write about them in our papers, we just call them compound 1. Or A, or make up some other name for it, and then draw the structure. So the name of an organic molecule is useful only to a point. The purpose of the name of a molecule is so that somebody else can read that name and draw the right structure. It's got to be unambiguous. So we're going to learn about how to do that to a point, but don't go down the what if rabbit hole. Because you'll always be able to think of something that I don't know how to name. And the kinds of things I've asked you on the study guide will be at the level that you'll be doing on the exam. But realize the exam's multiple choice. You're not going to be naming things from nothing. You'll be choosing among various options. Now, the naming of molecules is tedious, but it's relatively easy. And so I don't want to spend too much of our time in class. I'd rather talk about things that are more challenging and more important. But I do want to say just a few things about the traps people can get into with naming molecules. So you've got sort of three different parts of a molecule's name. You've got the suffix, and the suffix tells you what the highest priority functional group is. And there's in the study guide an elaborate list of priority rules. That's just scratching the surface. Fortunately, I have very little interest in knowing whether a carboxylic acid is higher or lower priority than an ester. So let me show you 3 different groups you can globally group molecules in terms of priority. And you're going to think in terms of number of bonds between carbon and a heteroatom. Z is a heteroatom. Z means anything other than carbon or hydrogen. Organic chemistry is very carbon and hydrogen centric, so when we say heteroatom, we mean anything other than carbon or hydrogen. So there are 3 basic groups. One has 3 carbon-hydrogen bonds. An example of this functional group, class of functional groups would be acids. But you could put other things here instead of the OH group, or you could put an amino group there. Then the second is 2 carbon heteroatom bonds. This would be like aldehydes and ketones. Do you see the 2 bonds to, by bonds we mean sigma and pi. We're not counting the double bond as one. And then lastly, the lower priority group is going to be just 1 carbon heteroatom bond. So this would include, say, alcohols. So notice I'm never really, I promise not to ask a question where you have to decide is the ketone or the aldehyde higher in priority. You could, there's a rule for that, but I don't care. Similarly, I'm not going to have you decide whether an alcohol or a thiol or an alkyl halide is higher in priority. Not interested. But if you can count, you'll be able to quickly recognize the highest priority functional group. Okay? That's shortcut 1. And there's a list of suffixes that you'll need to be familiar with. Then there's the root name of the molecule, and the root is going to tell you how many carbons, and it's going to tell you if there are any pi bonds, and if so, where they are, and also whether they are cis or trans. Do those words sound familiar to you? Are you aware of the possibility for cis or trans stereoisomers about a double bond? Yeah? Incidentally, why can't I get from this one trans isomer to the cis isomer by rotation around a bond? Yes? Pi bond locks into place because pi bonds are side-by-side overlap of p orbitals, and if you rotate around the bond, you have to go through a point where the p orbitals are orthogonal or 90 degrees with respect to each other, and they don't overlap, and you have to break the pi bond. Okay, that's just inherent in the geometry of the pi bond, so rotation around that bond requires breaking the pi bond, and it's difficult. Yes?
Sorry to backtrack half a second. Number 2 and 3, since there are 2 carbon to heteroatom bonds, are you counting the double bond to oxygen? Are you counting that as 2?
Yes, yes. So the question is 3 bonds, you only see 2, a double bond and a single bond. No, we're counting each separate sigma and pi bond. Yep, good. Okay, right, rotating around a carbon-carbon bond breaks, a double bond would have to break the bond first, and so though you can do it at elevated temperature, it's not really a thing at room temperature. So these 2 different molecules have the same formula, same connectivity, but different shape. We're going to call those stereoisomers, and stereoisomers is a topic that we'll get to in chapter 5. A real brief preview, the cis and trans situation is a particular kind of stereoisomer called a diastereomer. That's a word you don't need to know now, but you will in chapter 5. Cis and trans will work just fine for simple alkenes, where the double bond only has 2 non-hydrogen groups on either side. But of course, if you change it to having 3 or more non-hydrogen groups, all of a sudden, you still have the possibility for stereoisomers, but it's difficult to talk about them because cis and trans are relative terms. A group is cis to each other or to another group, or it's trans to another group. The reason we can use them up here is because there's only 2 groups to talk about. But when we get down here, if I called this one cis, you would have to know that I meant that I'm talking about the 2 carbon groups being cis instead of the chloro group, which is not cis to the other methyl group. And if I called this trans, similarly, you'd have to know I was talking about the 2 carbon groups. And that's a lot of explanation and a lot of words. And so we've got just a quick way to distinguish these 2 isomers. And the way you do it is you consider the 2 different sides of the olefin separately. And so I'm using a squiggly line. The olefin is another word for an alkene. I will use those 2 terms, olefin and alkene, interchangeably. Olefin is a name that organic chemists use for alkenes when they want to sound important. So there you go, I'm being pretentious. It's a name from the oil industry, but we'll use those interchangeably. Anyway, the squiggly line means I'm considering carbon A and carbon B of the alkene separately. I start with carbon A and I consider what 2 things are attached to carbon A, and I consider only the atoms that are attached. So I'm not going to worry about the other stuff, the methyl group, the hydrogens here, just the carbon, and here just the chloro. And then I ask, which one has a higher atomic number, or which one weighs more, which one is heavier? Notice it's atom by atom. I am not asking which entire group is heavier, because that would be too hard. That would involve lots of counting. We don't want to do that. So chloro is larger than carbon, so chloro becomes our landmark group on carbon A. On carbon B, again, we consider the 2 things that are attached to it. In this case, carbon versus hydrogen. Carbon versus hydrogen, carbon wins, is heavier, so it becomes our landmark group on carbon B. Then, and only then, do we worry about describing stereochemistry. If these 2 landmark groups are on opposite sides, we're going to call the stereochemistry of that alkene as E. This is from the German word entgegen, which I think means apart or opposite or something like that. I learned a funny German word the other day. I don't speak German, but my son and I were looking up funny German compound words, and one of them was Backpfeifengesicht, which being interpreted is a face in need of a fist. So a friend of mine said he was going to definitely use that with the deacons in Deacons Quorum. Anyway, E, opposite. Here, the 2 landmark groups on either side are on the same side, and we'll use the letter Z, which is another German word, I think, zusammen, for together or same or something like that. If you want a mnemonic device, Z means that the 2 landmark groups are on the same side. It's terrible. Okay, you can always think of situations that are more complicated. Let me just give you one here, and we'll work through it. You should practice this because this will come in handy a little bit later in chapter 5 when we start talking about chiral molecules and stereocenters. So the question you might be asking is, what do you do when the 2 atoms attached to one of the 2 carbons of the alkene are the same? And fortunately, we have a tiebreaker procedure, which again is tedious. It's not too hard to learn. You should practice it. I'll try to spare you the misconception. I'll try to identify misconceptions along the way. First of all, on carbon A, there's a clear choice. What is it? What's the landmark group? that carbon, right? Carbon, you're not considering the whole chain. You're just considering carbon versus hydrogen, carbon wins. Now, we consider carbon versus carbon, and it's a tie. So we have to do the tiebreaker procedure. And here is the tiebreaker procedure. All right, I'm going to write down all of the things that each carbon is attached to, and I'm going to write them down in order of weight. So carbon, I'm not sure what we want to name it. Let's do C versus D. I don't know. Carbon C is bonded to 2 carbons and 2 hydrogens. Carbon D is similarly bonded to 2 carbons and 2 hydrogens. Then I go down the list one by one, making comparisons, and if there are no differences, I haven't broken the tie yet. So carbon versus carbon, carbon versus carbon, hydrogen versus hydrogen, hydrogen versus hydrogen. It's still a tie, so we still don't know which is the landmark group. So we're going to go out to the next atom, E and F, and ask what they, make the comparison, carbon versus carbon. It's still a tie. So now we're in like the second or third round of tie-breaking procedures. We now ask, what are these bonded to? E is bonded to 1 carbon and 3 hydrogens, whereas F is bonded to 2 carbons and 2 hydrogens. We make the comparison one by one. Okay, that's a tie. Then here, finally, carbon versus hydrogen. Carbon wins. This is the landmark group. All right? That's going to take some practice. And so I encourage you to do that. And if you struggle with it, get help in your recitation section or come and work some problems with me. Yeah?
What happens if they're the same, like, symmetrical?
If they're the same, if they're symmetrical, then there's no stereochemistry to even talk about. Let me just illustrate that with this example. Is that a cis or a trans or an E or a Z alkene? You can switch the place here with here if you want, but it's just the same identical molecule. Yeah, so if you have 2 of the same group on one side, but they have to be the same all the way out, then you don't have to assign E or Z. You wouldn't need it to draw the right molecule. Yeah? Does that mean automatically shortcut longer group?
Yeah.
No. If, for example, I had put a chloro on that carbon, that one would have won earlier on. Yeah. So as I said, it's better to practice that than to necessarily talk about it a huge amount. Make sure you can get that. With the understanding that our priority groups or our landmark groups are there, what is the designation or configuration we would give to that alkene? Z, good. Zameside. All right. Then lastly, you've got prefixes. And the prefix is actually going to contain the Z information. That's annoying, but that's the way they do it. It would be easier just to put it near where the alkene is in the name. The prefix tells you about the location, identity, and number of other functional groups. All right, so let me just illustrate with an example, and let's continue with the one we've drawn here. Other functional groups, the highest priority functional group in this molecule is the carboxylic acid. So the suffix is going to be oic acid. The root should describe the number of carbons in the longest carbon chain, right? So I'm going to start with the highest priority functional group, 1, 2, 3, 4, and then 5 and 6. Then based on the number of, oh, did I, no, that's right. Did I skip? Yes. I skipped, yeah, that's embarrassing. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. Do you guys know the count from Sesame Street? Yes.
At B, if, let's say, it had gone down to a CL there,
Yeah.
would you have counted down that way? Would it had ended at B?
If I had had if this C had been a chloro instead of a carbon, we would have had no need for a tiebreaker procedure because chloro beats carbon.
Okay, but when you're counting the carbon,
Yeah, if this had been just chloro, you would have continued to count down the longest chain. Yeah. And as I said, you can always think of weird situations. We're going to call this group one of the other groups attached to the main chain. If you put other things here, the naming would be more complicated, and I don't know how to do that. So we identified 8 carbons. That means we're going to be looking at an oct kind of molecule. We would use octane if there were no double bonds. There is a double bond, so we have to call it an octene. And we need a number to tell us where the alkene is. And so we're going to use oct4-ene oic acid. Some people will, to make it more pronounceable, go 4-octene oic acid, and that works fine, but you can also do it this way. Sometimes if you put the numbers out front, it becomes a little bit ambiguous what you mean in here. Nevertheless, I promise not to give you a multiple choice between these 2 options and only one of them's right. Yeah?
Where did the OIC come from?
Oic acid comes from, it's just the naming rule that they chose. So technically this is ethanoic acid.
Is it always OIC?
Yeah. I don't know why. Actually, we're not even going to bother with this. We'll just call this acetic acid or vinegar. But, yeah. Okay. So we've now got our suffix and our root. Yes?
Where'd you get the 4 from? Was that, where's it?
The 4 is the first atom of the pi bond. All right. We've got, let's see, everything except now prefixes for the location, identity, and number of other groups. The only thing we've got here is this 2-carbon group on carbon 5. So we're going to call that 5-ethyl. And then, of course, we would need the Z in front. If you only have one alkene, you don't need to put a number in front of this Z because it's automatically implied that this Z refers to this alkene on carbon 4. If you had multiple alkenes, you would need numbers before each designation. Yeah?
What happens if you start counting carbons from the other side?
If you start counting carbons from the other side, you'll get the numbers wrong. Other than that,
How do you know which side to start counting?
you start from the highest priority group. Yep. Now, I also don't really care about which way you number because as long as you do it consistently, somebody could draw the right molecule from your name. So, for example, I'm not going to give you a problem where I say, let's call this where I give you a choice of, let's see, what would the other option be? Where the carboxylic acid is on carbon 8 and the alkene is on carbon 1, 2, 3, 4. Anyway, I'm not going to give you the choice between 2 legitimate numbering schemes. But technically, yes, you start with the highest priority functional group. Yes?
What's the alkene on carbon 5, I think you're talking about? That's why you add the ethyl?
No, sorry, this group?
You mentioned an alkene. What is an alkene?
The alkene I'm referring to is this double bonded group here.
Does that just mean a double bond alkene?
An alkene is a molecule that has a carbon-carbon pi bond in it.
Oh, okay.
Yep. If it were a triple bond, we'd call that an alkyne. You'll learn that as you look at the study guide. Yeah.
So when you're numbering a molecule that has multiple double bonds with your Z, do you put the number like the 4 and the 5, or would you just put like 4?
The question is if I'm numbering a molecule with multiple double bonds, I only need the first lowest number, right? So if I had another double bond out here, for example, I would call that oct 4, 7 ene oic acid, and I would then need to have a 4 out here for the designation there. And then, okay, so I think that's a sufficient level of detail to get you to work on the problems that are in the study guide. Again, you could go deep what if on me, but get a feel for the kinds of questions I'm going to be giving you first, and then you can come ask me. Yeah?
If you're using Z referring to the cis isomer, then wouldn't it be 5 propyl instead of 5 ethyl?
If you're using Z to refer to the cis isomer, wouldn't it be 5 propyl instead of 5 ethyl? The designation of the double bond, its configuration, actually doesn't have anything to do with what is the longest carbon chain. The reason we're naming this as 5 ethyl instead of 5 propyl heptanoic acid is because the longest carbon chain goes this way. So Z and E or Z isn't going to tell you which way to count your chain at all. Yep. Uh-huh.
Should we just memorize the function groups as their suffixes from the...
So suffixes and prefixes, memorize or at least recognize. You're going to use the suffixes only for the highest priority functional groups, so the ones at the top of the page are going to matter more than the ones at the bottom of the page. The prefixes you're going to use more for the lower priority groups, so those will be at the bottom of the page more important than at the top. Okay, give that a try, and then get some help in your recitation section. Come talk to me and work through some problems. Don't go down the rabbit hole, and don't spend too much time studying nomenclature instead of other important things. You need to know enough to do the kinds of problems that I've shown you on the study guide and on the practice exam, but more than that is not useful. Okay. I want to talk now about why we care about functional groups in the first place. And that's because they're so related to things that we can taste and smell. And also, interactions between functional groups are related to various phenomenon that we observe in our everyday life, from why you need eggs when you're mixing oil and water in a recipe, to why the organic, all-natural peanut butter has a layer of oil at the top of it, but Skippy doesn't. All of these things have to do with the way functional groups interact with each other. So let me just say a little bit about some of the most important functional groups. Carboxylic acids. This is acetic acid, and this is in vinegar. And you have likely tasted it before. It tastes tart. Okay? Kind of sour. Another carboxylic acid that you have experience with. Excuse me, I get all verklempt when I start talking about carboxylic acids. Just kidding. Come on. This is citric acid. and that's responsible for the tart, sour flavor of citrus fruit. It's sometimes also used as a preservative when you're canning fruit. Do I want you to memorize the structures of acetic acid or citric acid? No. I just want you to know that you've encountered these things in your life before. Another functional group is where you take the carboxylic acid and you put, instead of an OH group here, you put another carbon group. And this is an ester. And esters are found all over the place, though the place where you most likely encounter them in your day-to-day living is food additives for flavor. So those of you that take the 353 Organic Lab are going to make an ester that smells either like strawberry or banana. I forget the structure of the one that looks like banana, so I'm just going to look it up real quick here. I'm just going to type into Google banana ester. Boom. Okay, there we go. So if you take this ester, and it's called isoamyl acetate, notice that I just gave you a totally non-systematic and nonsensical name for this molecule. That's why we don't bother too much with nomenclature. This one smells like banana. In contrast, let's see, let me look up the strawberry ester. I wasn't planning on this necessarily, so all of a sudden here I am. This one's a little bit more complicated, so we won't worry about it we won't worry about it per se. It's got a functional group there that we won't deal with till you get to chapter 9 called an epoxide, but here's the ester portion, and this one smells like strawberry. Okay. So yeah, esters are smelly compounds. Yeah.
So ester, like, is like that whole molecule is an ester. Is it not just like the O in the middle, like connecting to?
Right. So how do we name the molecule? Do we call the whole molecule the ester, or do we just worry about this functional group, which is the ester? Yes. If the molecule's small enough and just has one functional group in it and it's an ester, we'll call the whole molecule an ester. If the molecule is more complicated, we'll talk about the ester functional group. Yeah. This is also, you have a great chance to start naming some of your children after organic molecules. This is an ethyl group, so this is called an ethyl ester. Right? That'd be a nice name. Okay. Actually, one of my colleagues has a daughter named Esther, and he's an organic chemist, so I'm sure there was a little bit of joking there. But she told him, "Daddy, I know why you named me Esther." And he says, "Why?" "Because I'm the smartest and the prettiest and the bestest." Whatever. Yeah. Say it again.
My grandma's name is Ethel.
Your grandma's name is Ethel. Okay, so should you have a daughter in your life and you want to name her after your grandma, I highly suggest the middle name Esther.
She doesn't go by it.
Okay. All right. So, following nomenclature, we would call this ethyl ethanoate. I don't like naming esters by nomenclature, so we're not going to do it. Yeah. Okay, aldehydes and ketones. There's some important ketones and aldehydes that you need to know. One of them in your life, one of them is glucose. It's sort of a hidden aldehyde. What is this weird thing I've just drawn? That is a chair conformation for a cyclohexane-based molecule. Please don't worry about that. This is called beta D, because we'll get to that later. This is called beta-D-glucopyranose, or glucose for short. It has a closed chain form that's in equilibrium with, don't panic, I'm just illustrating the aldehyde, okay? And when I do this, people are like, oh, do I have to know all of these molecules? We're not about memorizing things. This class is more about what you can do than what you know. This is the open chain form of glucose, and it's got this aldehyde functional group. And you're going to see in 352 that aldehydes are pretty reactive. One aldehyde you may be familiar with if you've ever worked with like cadavers or other biological samples that have been preserved is formaldehyde. And so you might have the idea that aldehydes can do things to biological tissues, and this can happen with glucose too. Yeah?
So there's a lot of OHs on there, so which one would be the highest priority functional group?
We don't even bother with the IUPAC nomenclature for this molecule. When you get to 352, they'll teach you how to name sugars. It's not as bad as you think, but this is glucose is it's this carbon here. Notice it's got 2 bonds to oxygen, and that's a clue that it's a masked aldehyde. Again, don't worry about that chemistry. That's 352. I just wanted you to see that glucose is an aldehyde, and this is one reason why your blood glucose level needs to be regulated. If it's too high, your aldehyde on your glucose is going to start reacting with biological molecules. How many of you have heard of, what is it, H1C, or what is it, the thing that's monitored for diabetes? Anybody? A1C? A1C or something like that? That's monitoring the addition of glucose to one of the hemoglobin proteins in your red blood cells, and it's a measure long term of how high your H1AC. I'm getting it totally wrong, but you guys you have the idea. Anyway, it's a measure of how high your blood glucose level has been as a function of time. Let's see. I think those are the ones I wanted to talk about. I suppose there's this one, which is consumed in large amounts at other universities. There's this one, which is called isopropyl alcohol, or 2-propanol, and this is rubbing alcohol that you can use to disinfect things. You don't actually want to drink this, that would be bad. Right. And you also don't want to drink methanol. This is just a simple alcohol. This is, it's called wood alcohol because you can get it from fermenting wood. The phrase blind drunk came from a time when people would distill their own alcohols, probably during the early days of Prohibition and moonshine and stuff. And if the boiling point of methanol is lower than the boiling point of ethanol, so you can separate them that way. But if you don't do a good enough job and you consume enough methanol, if it's mixed in, it will make you go blind. So don't drink alcohol, but especially don't drink alcohol that's been distilled in the woods. Yeah?
What designates something like all that like?
The all at the end is when you have the highest priority functional group is the OH group, or the hydroxy group. Yep, that stands for alcohol. And that's what we call all of these functional groups. Okay. Another one that you may have day-to-day experience with is this one. This one's called ethylene glycol. Again, don't memorize these names or structures. This is antifreeze. And it doesn't, because of the carbons, it has a lower melting point, or much lower temperature melting point than water does, and so it can prevent water from freezing in your car. It also tastes and smells sweet, which is why you don't want to leave it out in the presence of animals or small children. Yeah?
Why is it ethylene when there's
Why is there ethylene when it's not a double bond? Because I think you can make it from ethylene. Understand that chemistry evolved over a long period of time and we didn't know a lot, and so a lot of old names have simply stuck. And sorry, yeah.
How do you keep one alcohol from turning into another alcohol or interacting with each other over time?
How do you keep one alcohol from turning into another alcohol? Well, I mean, in the absence of other molecules, it's going to remain unchanged. The issue was that in the fermentation process, you could generate both of these, and so you would need to separate them. And you have to do that based on their physical properties. And we'll actually talk about that. But for example, I know that the boiling point of ethanol is lower than the boiling point of methanol. That has to do with the number of carbons for reasons that we'll discuss. So if you take a mixture of the two of them and you're very careful and turn up the temperature slowly, it starts to boil at first. Presumably the methanol should come off first. So you wait there and you do that until all of the methanol is gone, and then maybe all you have is ethanol. Or maybe there's still a little bit of methanol in there, enough to make you go blind. So like I said, don't distill your own whatever. Okay, so now we've got a sense for where we encounter these functional groups in day-to-day living. There's a lot more we could talk about, but we'll leave it at that. I want to talk now about the interactions between molecules that are enabled by these functional groups. We're going to call these non-covalent interactions because they don't involve sharing of electrons in a covalent bond. This is a huge area of organic chemistry. It's an area that interests me immensely. I could easily take the next 5 to 10 lectures and just spend it all on this, which would be awesome. But my pet favorite things don't need to become yours, and so I'll try to make this not about me, but rather about what you need to know. All right, non-covalent interactions involve are interactions between charges or partial charges, either permanent partial charges or temporary ones. So we have on this list of potential partners in non-covalent interactions, ions, which are point charges. Basically, you can think of them as point charges. We're talking like sodium, chlorine, potassium, other ions. You've got dipoles. Dipoles, you learned in Gen Chem, are a non-uniform distribution of charge along a line. As an example, one dipole might be in HCl, chloro being more electronegative than hydrogen. There would be a partial positive charge on hydrogen, a partial negative charge on chlorine. Why is that bond polarized? Because electrons near chlorine are lower in energy because of its increased electronegativity relative to hydrogen. And let's see, we will sometimes draw the dipole as an arrow with a plus end on the positive side. And these can interact with ions or with each other. The most famousest of dipoles is water, is the one in water. You have these individual oxygen-hydrogen bonds with plus positive or partial positives on hydrogen, partial negative on oxygen. Dipoles happen to be vector quantities, so the individual bond dipoles can be added to give you this overall dipole for water. You can have dipoles interact with ions or with other dipoles. Another less familiar one that I do want to talk about, it's not in your text, but it's important, is something called a quadrupole. There are reasons for that. I don't know necessarily why. A quadrupole is a non-uniform distribution of electron density in 3 dimensions, but not along a line. So, introducing benzene. This is a hydrocarbon, and it's a nonpolar solvent. Now, sp2 hybridized carbons are more electronegative than hydrogen. That's not an obvious comparison, but you know that there can be differences in electronegativity for sp2 versus sp3 carbons because of the S character. So you can see that if I had partial pluses on a hydrogen and a partial negative on a carbon, you might think about an individual bond dipole, but that would be canceled out by the bond dipole on the other side that's directly opposite it, symmetrically, right? And you see how those 2 dipoles would cancel each other out? That's true for all of the carbon-hydrogen bonds. So it is absolutely correct to say benzene is nonpolar because it doesn't have a dipole. However, it is not correct to say that benzene has a uniform distribution of electron density, because what we've just described is a system where the carbons are electron rich and the hydrogens are electron poor. We'll use the color red for the area of benzene that is electron rich, the face of the ring, and we'll use the color blue for the part of benzene that is electron poor, which is the edge of the ring. And if we looked at benzene from the side, whoops, I'm going to try to illustrate this, sort of looking at the molecule on its side. Here are the pi bonds. It's the either face, top or bottom of this ring, that's going to have partial negative charge, and it's going to be the edge of the ring that has partial positive charge. So you might expect that this quadrupole could interact with ions and dipoles, and in fact that happens all the time. As an example, you can put a potassium ion in the gas phase near a benzene molecule, and the potassium ion, I don't know why we're bothering to color, the potassium ion will actually interact and sit down on the face of the benzene ring. It's attracted to that negative charge portion. That's actually, I mean, that's sort of a mind-blowing thing that can happen. That is called a cation pi interaction, because the ion is interacting with the quadrupole that's present because of the pi bonds in the benzene ring. Okay, I wouldn't have expected you to derive that from nowhere, but that's the kind of thing we'll be looking at. The one other thing we need to mention on our list is the induced dipoles. And I want to just briefly preview this. Induced dipoles are difficult to understand, but they really refer to what can happen in a molecule where the electron cloud can temporarily distort itself to accommodate its nearby environment. So you would expect this hydrocarbon to be basically nonpolar, and you would expect there to be sort of a cloud of electron density in the various bonding orbitals that surround this molecule. And overall, you don't expect a permanent dipole at all. And you're right, this 1, 2, 3, 4, 5, 6, 7 heptane is completely nonpolar. And yet, instantaneously, at any given point in time, one side of the heptane molecule can gain a small but meaningful partial positive or partial negative charge, and the other side can gain a small but meaningful partial positive charge. It's temporary, it's instantaneous, it's just as likely to switch back in the next instant, but the fact that it's not uniform is important, and we'll talk about that next time. Thank you, and have a good day. We'll see you Friday.